Great. Well, thanks very much. So what happens in the Arctic does not stay in the Arctic. We'd like to make a recommendation for a totally new paradigm in modeling sea ice, permafrost, and other multi-scale systems. In particular, building from the bottom up, from the micro to the macro in the climate system, as you see this incredible range of scales in the sea ice system. So sea ice plays a very important role in the climate system in reflecting incoming solar radiation and basically acting as Earth's refrigerator in the polar regions. However, that beautiful white icy reflective surface is melting and disappearing. We've lost almost half of the summer Arctic ice pack, not in 10,000 or a million years, but in the last 20 to 30 years. To put this in some geographical perspective, well, that's kind of where it was, the median over the early part of the satellite era, and then here's kind of where we are about 2 years ago. Indeed, the Arctic is ground zero for climate change. This is how much we've lost compared to the land mass of the United States. Modeling of large-scale sea ice dynamics has been dominated for decades by top-down, coarse-grained numerical models with grid sizes on the scale of 25, 50, 100 kilometers, based on a framework that was developed almost half a century ago. And here are some of the world's best global climate models, but here's the actual data. The idea was they were not showing rapid enough declines in the sea ice pack. Part of the reason is sea ice is a very complicated multi-scale composite material where you need to work from the bottom up. The sub-millimeter scale brine inclusions, the centimeter scale polycrystalline structure, the brine inclusions form these channels, Arctic melt ponds on the surface, pressure ridges. The sea ice pack itself can be viewed as a granular composite of flows that range from centimeters up to tens of kilometers. When you're dealing with complex composite structures, you're interested in the effective or overall properties on larger scales, such as the effective conductivity of a two-phase composite of a good conductor and a bad conductor. Turns out these are very famous, storied problems with a long history, going back to Maxwell and Einstein themselves. Here's showing some of the smaller scale structure, that the self-similar structure, and there's showing the 10 centimeter scale, 1 centimeter, 2 millimeters, and showing these inclusions occupied by all the incredible biology. There's entire ecosystems in these inclusions themselves. So here's some of the impacts of permafrost that basically as we're getting thawing permafrost in the Arctic, getting all kinds of, and showing bubbling up methane and so on, and all the kind of damage that can be done. So dramatic changes in the Arctic sea ice and permafrost impact the climate, ecology, economics, infrastructure, transportation, and human activities in the region, but also have cascading effects in the rest of the world, and the US in particular. Weather and precipitation patterns, storm tracks, skiing in the western US, cornfields in Iowa, floods and droughts, ice storms in Texas, and so on. These large-scale coarse-grained models built from the top down, they're useful for long-range projections, but have become increasingly complicated as more and more is accounted for, and are not so well suited to studying smaller-scale processes and critical behavior where fine-scale structure is essential. There's huge gaps in our knowledge of sea ice behavior. In particular, the features of sea ice that I mentioned before, they determine the large-scale dynamics and behavior, the brine inclusions, polycrystalline structure, brine channels, the flow sizes, oceans, waves breaking up the ice, melt ponds, ridges, and so on. We need to incorporate these. How does this affect the macroscopic behavior? So the proposal is we want to build a new paradigm for sea ice modeling built from the ground up, from micro to macro, but and we recommend that a community be developed with sufficient critical mass and contributions from many disciplines to overcome this historical inertia over the last 50 years to build a new paradigm of modeling sea ice and other multi-scale components of the climate system, such as permafrost. We look to the successes of statistical mechanics, solid state physics, material science, mathematical homogenization. These are all built on the same idea, from building up from the micro scale to the macro. We want to build a modeling approach that reflects the actual structure, not sort of assumptions about from the top down. Can we rigorously analyze key phenomena over all scales, not just scales that exceed resolutions of tens of kilometers? And then this approach would apply to permafrost and other multi-scale systems. We'd like to create interdisciplinary teams of researchers, engineers, modelers, experimentalists, stakeholders, and supporting staff with many different kinds of relevant scientists led by mathematical and computational scientists, data scientists, geophysicists, and so on to build these models and test them and so on. The resources we needed on the order of 10 million per year for 10 years, 2 to 3 cycles of 3 to 5 year awards for smaller and larger interdisciplinary multi-institutional teams for both pilot and exploratory, as well as the full research projects. Establish a $10 million center institute to support this large scale research project with labs, imaging and computational support, and so on. And then also, it would be important to inform these models and validate them. So we would like to have 2 expeditions over the 10 years to collect data and validate these models. Ultimately, the impacts, fundamentally new mathematical ideas on multi-scale methods and computational tools, improving data collection, data science methods, storage, imaging technologies, the ability to improve our projections of the cascading effects of the sea ice loss and permafrost thaw on precipitation patterns, freshwater ability, and more broadly weather and climate situations, ultimately will affect socioeconomics, geopolitics, energy policy, national security, food security, and we hope to make big impacts on these types of things. The center research projects will be part of the action to mitigate and effectively respond, potentially reverse sea ice loss and permafrost thawing. There will be lots of educational impacts, interdisciplinary experience. We want to get math students up to the Arctic. Why now? There's been the largest Arctic expedition in history has just finished. We have early successes in the micro to macro idea at the material level. Hey, the ice is melting to work. So finally build models of sea ice, permafrost, and other multi-scale components of the climate system from the ground up, from the micro to the macro. Thank you, and thanks to NSF and SIAM.